So now we are discussing about optimizing training loops. We are discussing two major techniques for reducing the GPU memory usage during training. That is mixed precision training and gradient accumulation. These techniques are especially important when your GPU is limited, your model is large, or you want a large effective batch size without upgrading hardware. Why training optimization matters? Deep learning training consumes a lot of memory because the GPU must store model weights, activations, gradients, optimizer states, mini batches. As models become larger, memory becomes the bottleneck. The lessons that we're going to acquire here uh, is to reduce memory usage, maintain accuracy, and still train effectively. Let's talk about the mixed precision training. Normally, deep learning uses float 32, which is 32-bit floating point precision, accurate, but memory heavy. So, by the way, um, in what we mean by the precision, normally in the deep learning, we convert the original value into the floating point. Um, there is like there is accurately 32 floating point accuracy, then there is 16 like what we are using here. Like we have the float 16 or 16-bit, that's a lower memory, and float 32 is 32-bit, that is stability when needed. Basically, the the larger the floating point, that's that's more accurately um, determine the original value, because in actual computation we use the floating point. So the idea here in the mixed precision training is use float 16 wherever possible, automatically switch to float 32 for numerically sensitive operations. So what does float 16 actually do? A float 16 number uses half the memory of float 32, faster tensor operations on modern GPUs. So like for example, the precision is float 32. The memory per number is 4 bytes, while the float 16 is 2 bytes. So if a tensor originally needed 1000, so therefore in the float 32 we have the 4000 bytes, because 1000 times 42, and float 16 needs only 2000 bytes. That's 1000 times 2. That is roughly 50% memory reduction. Why not use float 16 everywhere? Because float 16 has lower precision. That's like what I uh, tell. Smaller numerical range. Because float 16 is smaller numerical range. Some computations becomes unstable because it lower precision. Does not accurately convert the original value to the floating point um, accurately. So gradients may underflow, losses may explode, updates may become inaccurate. So mixed precision keeps important operations in float 32 automatically. So mixed precision in PyTorch Lightning, uh, like we use a precision equivalent 16 mix, meaning mixed precision mode, automatic casting between float 16 and float 32, and the standard training uses precision 32, uh, precision equivalent 32 true, which means full float 32 training. Next is gradient accumulation. Normally, training works like this. First is from the forward pass, complete loss, backward pass, update to weights, and repeat. This happens after every mini batch. So the problem, large batch sizes improves training stability, but large batches require large GPU memory. Example, batch size 64, so the memory usage is lower. But when it comes to 256, that's much higher. So the solution is gradient accumulation. Instead of updating weights immediately, the process several mini batches, accumulate gradients, then update once. So here's the core idea. Suppose the batch size is 128 and accumulation step is 2. Then effective batch size is 128 by 2, so that is 256. That's the effective batches. That is the total total batch in once update, because we update once you accumulate all the gradients. This means GPU only loads 128 samples at a time, but gradients behave as if batch size were 256. That's a huge memory savings. So step-by-step example, the lesson gives these configurations. Actual batch size is 128 and the target effective batch size is 256. So we compute it, we divide the target effective batch size to the actual batch size. 256 divided by 128, that is 2. So the effective batch size is, the gradient accumulation is 2. So meaning we run 2 forward or backward passes, some gradients, and update weights once afterward. Here's the important distinction: actual batch size, the number of samples physically loaded into GPU at once. Example, batch size is 64, and effective batch size, the total samples contributing to one optimizer update. So the batch size is 64 and gradient accumulation is 4. So when we multiply 64 by 4, so we will have the effective batch size, that is 256. Why this saves memory? Without accumulation, 256 samples loaded simultaneously, huge memory usage. With accumulation, 64 samples loaded 4 separate times, much smaller memory footprint. So the GPU never holds all 256 simultaneously. So here's the experiment setup. So we have test six configurations: the technique, position, batch size, accumulate steps, and effective batch. Like for example, we have the technique. So this is the baseline. So we the 32-bit precision, batch size is 256, accumulation steps 1, and effective batch is 256. We have the mix precision, 16 mix, 16 precision, and batch size is 256, accumulation steps 1, and the effective batch is 256. Gradient accumulation is 32-bit, batch size is 128, and accumulation step is 2, and effective batch is 256. And gradient accumulation is 32-bit, and the batch size is 64, and accumulation step is 4, and effective batch is 256. And mix plus accumulation is 16 mix, and batch size is 128. Accumulation steps is 2, and effective batch is 256. So the mix plus accumulation and its precision is 16 mix, and batch size is 64. Accumulation step is 4, effective batch is 256. So notice all have effective batch size is 256, making comparisons fair. Why keep effective batch size constant? Because changing batch size changes training behavior. If every setup uses effective batch size 256, optimizer sees same number of samples per update. Comparisons become meaningful. So results accuracy. So it reports the baseline accuracy is approximately 72%. All optimized methods stay within 1%, meaning memory optimization did not hurt accuracy significantly. So here's the memory usage. The key findings: mixed precision is reduced memory because float 16 tensors use less space. Gradient accumulation produce even larger memory savings because smaller per step batches fit more easily in memory. And combined techniques is best overall memory efficiency. So here's the main takeaways. Accuracy stayed stable. Optimization techniques did not significantly reduce validation performance. Next is gradient accumulation is mainly a memory trick. It simulates large batches without loading them all at once. Next is mixed precision gives additional savings, especially useful on modern GPUs with tensor cores. So, and combining both is powerful. Very common in training modern models. Examples is LLM training, diffusion models, vision transformers. So, in real world perspective, so it's emphasized there is no universal best setup. Your choice depends on GPU memory, training speed, accuracy goals, hardware, and model size. So the practical rule of thumb: if GPU runs out of memory, try mixed precision first. Next, then gradient accumulation, and then reduce model size if needed. So think of it like mixed precision is used smaller number format to save memory. Gradient accumulations pretend we trained on a larger batch by splitting it into smaller chunks. So the final summary. So model training optimization is largely about balancing memory, speed, and stability. So the two major tools are the technique mixed precision and the gradient accumulation. So mixed precision, main benefit is lower tensor memory plus faster compute, and gradient accumulations simulate large batches with small memory. And